Hello class, welcome to your second video lecture on chapter 22, acid-base chemistry of carbonyl compounds. Today we're going to take a deeper look into the enolate ion and the chemistry related to it. Here is our chapter theme by Marvin J. Ashton. Everything is given by God. All talent, creativity, ability, insight, and strength comes from Him. In our own strength, we can do nothing. So please take some time and reflect on that statement. Recall that God created you and that He also created this subject, and that it'll do you best to rely on Him as you study this material. Here's our learning objectives, just revisiting all these. We've already taken care of acid-base reactions and why ketones have a higher acidity, and we've introduced enol, keto, tautomerism. Today, I'm going to talk about these three learning objectives: isomerization and racemization. We're going to understand how to predict which enolate ion will be formed when using unsymmetrical ketones, thermodynamic versus kinetic. We've heard of these terms up to this point in class, and we were looking at the conjugated dienes back in chapter 10. And finally, we're going to discover the difference between using LDA as a base versus KH. And as I already mentioned, our final video lecture will take a look at some of the reactions, especially looking at the halogenation of various ketones and including the haloform reaction. All right, so in this slide, we're going to look at isomerization reactions of tautomerism. So if you don't remember what tautomerism is, you may want to go back and look at the first video lecture of this chapter, okay? Isomerization is considered to be the interconversion of isomers, and isomers is a word you should know at this point, but if not, go back and check your Organic 1 notes to see what that means. But isomerization is the interconversion of one isomer to another, okay? And remember, you have constitutional isomers, and that's exactly what we're going to be looking at in this slide, but you also have optical isomers where you might interconvert R to S and S to R and whatnot, or that sort of thing, okay? And tautomerism plays an important role in isomerizing many biological molecules that contain aldehydes and ketones, and one in particular that I want to teach you is the carbonyl transposition. It's an isomerization process seen in carbohydrates, and as I go through this mechanism, I do want to make you aware that you are required to know this, and I'm going to show it on a molecule called glucose 6-phosphate going to fructose 6-phosphate. It's the second step of glycolysis, but I can use any carbohydrate virtually and ask you for the mechanism, so long as you understand the pattern of this process. So let's take a look at this. So this is going to be called carbonyl transposition. So carbonyl is a C double bond O, and we're going to be moving it from this carbon to the next carbon, okay? And that's exactly what's happening. You're transposing it elsewhere. And let's take a look at what the mechanism might look like on a molecule called glucose 6-phosphate. So it's an aldose. And then I'm just going to shortcut a little bit. CH2, OPO3, 2 minus, so that's D glucose 6-phosphate. And then what we have is OH. Okay, so the very first step in this mechanism is a tautomerism reaction. And what's going to happen is we are eventually going to wind up with this intermediate. It's called an enediol intermediate. You may want to know that word. I'm not drawing this in sp2 format, by the way. I'm just trying to draw out the important parts of this mechanism, but I am intentionally neglecting the hybridization bond angles. So just make a mental note of that I'm not drawing this as I should. It's an OPO4. This is called the enediol intermediate. So I'm going to show you the acid catalyzed tautomerism. You may want to try this using base because it goes through the same thing. Well, it would finish off with the same product is what I'm trying to say, but just in terms of acid, let's use that particular mechanism. I'm going to try to color code this for you so it's easy on the eyes. So we have acid in there, H3O plus, hydronium ion. And what's going to happen is it's going to grab the H, that carbonyl group is going to grab that H, yielding water. Okay. And let's see, the next step is going to show you that, sorry, I ran out of space. I'm going to show you the intermediate in this step. It's going to be okay, so that's the intermediate that you just had, and then you're going to have water come back in. This is just based on the acid catalyzed tautomerism reaction that we saw in the previous lecture. And this water is going to grab that H right here, which gives you that enediol intermediate. So that's the first step. You make that enediol intermediate. And then next what we're going to do is we are going to finish off and do the carbonyl transposition. So what's going to happen is we are going to make this. So it's a CH2OH there at the top. You may recognize this as a ketose. And this is fructose 6-phosphate. And that's the overall conversion. You go from glucose 6-phosphate to fructose 6-phosphate, going through an enediol intermediate. You go from an aldose in the glucose to a ketose in the fructose, and you may notice that this carbonyl group was literally transposed by one carbon right here. It's right on the aldehyde at the very top carbon, and then it moves down the line by one. The question you may be asking yourself is, how did this last step happen? And I'm going to show you. So you know that you need to form this carbonyl group right here. And so what's going to happen is, I wish I had more room on this slide, but essentially, let me do this. Look at this middle structure, the enediol intermediate. And I'm going to show you that after the process where water, you look at the top right screen, where water plucks off that proton to give you the enediol intermediate, you're left with H3O plus, right? And so there is some H3O plus floating around right here in this enediol intermediate. And so what's going to happen is this OH is going to use its electrons, drop down right there. Then that double bond is going to reach out and grab one of the protons from the hydronium, leaving you with water and intermediate. Now, if you look at the right-hand corner, or the right structure, the fructose 6-phosphate, you may notice that the resulting structure of such a transformation is this. So I accidentally hit a button that made it continue the slides right in the middle of what I was saying. So hopefully you can follow what I was trying to say. So essentially what you had was you had this enediol intermediate. And you had these series of H's and OH's that we're used to. And I said that you had some hydronium in here. Hopefully this is more clear now that I have more room, so maybe the glitch was a blessing. I know I changed up colors as well. So what's going to happen is these two electrons from that particular oxygen is going to reach out and grab protons from the water, which would yield the following structure. I'm just going to consider that R group at this moment because it's really not important for this reaction. And then the very final step to get you to the final product would be you take the resulting water from the previous step, and it's going to deprotonate that hydrogen that's sitting there on the carbonyl group. There you go. And then what you wind up with is that fructose 6-phosphate. So that's to finish off the mechanism. I hope that that was clear to y'all. So here's a good exercise. Well, also I encourage you to try it using the base catalyzed mechanism as well, which kind of goes through a different series of steps. And so make sure you can do the carbonyl transposition using both acid and base, and make sure you look up the mechanism for each. All right, so during glycolysis, the enzyme catalyzes isomerization of glyceraldehyde 3-phosphate. We call that G3P, produces dihydroxyacetone phosphate. DHAP is what we call it. Propose a mechanism for this process in aqueous solution catalyzed by acid. And so this is a pretty simple and straightforward example. Remember that CHO is an aldehyde. Okay, so I'm glad that they used a small molecule in this case. So the way it works is you take your glyceraldehyde 3-phosphate, remember, the first step is that you protonate it at the carbonyl group position. Which would yield the positively charged oxonium ion. Which then the water can act as a base in this step to deprotonate there, giving you your enediol intermediate. Okay, and then your next step is going to have hydronium. Those 2 electrons come down. That grabs that to give you this molecule. That's not a stereocenter, sorry. And then water comes in and finishes off to give you the product. There you go. That's the end. So practice that mechanism, and again, I encourage you to try it using base. So here's another type of reaction seen based on tautomerism. It's called racemization. Okay, so what you're doing is you're making a particular and antiopure stereocenter racemic. Okay, so as it turns out, when a stereocenter, recall what a stereocenter is, it's an sp3 hybridized carbon that has 4 different atoms attached to it. Okay, so it can have a certain spatial arrangement that is very specific to it. And so when a stereocenter is next to a carbonyl group, alpha to a carbonyl group is how we might say it, the enantiomerically pure substance becomes a racemic mixture. It's actually a big problem when in the presence of acid or base. So an enantiomerically pure means a single enantiomer, only one of them. Racemic means a 50-50 mixture of enantiomers. You may recall that from Organic 1, an important concept that we went over. The reason you racemize a stereocenter alpha to a carbonyl group when in acid-base conditions due to tautomerism is because the sp3 carbon that was a stereocenter becomes sp2 in that enediol intermediate, lacking a stereocenter, and then reforming the ketone would result in a racemic mixture. Let's take a look at what we might see. Recall that a phenyl group is a benzene ring, and let's say we had this particular stereocenter. It's a methyl on one end, and you have an ethyl right here. And we're going to mix this with a little bit of aqueous acid or base. And for this purpose, because I've already shown you the acid mechanism a couple times in this slideshow, let's try it with base. just using base for this slide, but I want you to know that it can happen with acid or base. So let's take a look at what happens in base. So let's act like it's hydroxide, okay? OH minus. Okay, so what it's going to do is it's going to deprotonate the proton. That's alpha to the carbonyl group right there. And that's going to go here. That's going to go there to generate the enolate ion. Recall that there is a resonance form. Now, what I also want you to know, I'm just going to go ahead and draw that resonance form for you. What I want you to know about this particular structure that I just starred is right here used to be a stereocenter, but now it's sp2, and you just ruined that stereocenter. It's no longer present. You went from sp3, where you have a stereocenter, 4 different atoms attached to an sp3 carbon, and now you're sp2 and you're trigonal planar. You're flat. You have no tetrahedral 3-dimensional structure in that regard. So you just ruined your stereocenter by doing that, okay? Of note, I just want to make you aware that there was only one position I could have deprotonated in this molecule, okay? They were very clever in designing this substrate, that a phenyl group has no alpha proton on a carbon, or alpha carbon with a proton. And anyways, I just wanted to make you aware of that. So the one that I deprotonated using the hydroxide was the only available one I could have used. Okay, the next step in the mechanism, and again, we might call this achiral, lacks chirality, achiral. Okay, the next step in the mechanism, you may recall, is going to be the reforming of your ketone. So that's going to come down, and that's going to come out and grab. In this case, after your hydroxide reaches out and deprotonates in the first step, it becomes water. So now it's going to go in the reverse direction and deprotonate water to give you hydroxide. And sure, you just reformed your same molecule, but notice now it's racemic. Okay, I have no need to draw a stereocenter, any dashes or wedges, because it's, because it's sp2 right here. It's planar, so it doesn't have a preference as to which side it reforms. It's just going to be R and S in a 50-50 mixture. And so here's the mechanism of how this might occur. Okay, so you start with this enantiomer substance. You're so happy you just made the stereocenter, and then you accidentally mix it with acid or base in an aqueous environment, and then all of a sudden you start realizing your product is not enantiopure anymore. Well, it's because in the reaction flask it's doing this and you don't even realize it, and once you do realize it, you're very upset about it because most drugs are enantiopure. All right, so I just wanted to bring to mind that racemization is a big problem. In fact, here's a drug. It's called R-thalidomide. It was marketed back in the late 50s, early 60s, came from Germany, I believe, and it alleviated nausea associated with morning sickness. And it was the R enantiomer. It's called thalidomide, and here's the structure of it. And notice right here, you have a proton that's alpha to a carbonyl group, or on a carbon alpha to a carbonyl group, and it's R, so it's chiral. Okay, it's completely enantiopure. And that's the version that helps you, okay? Well, whenever you ingest it in your body, it goes through various acid or base environments, and it actually racemizes to an achiral enol form, okay? Here's your enol form right here. Remember the vinyl alcohol? And then it just reforms the ketone that you originally had, except for it goes to the S, okay? The S-thalidomide. You racemize the stereocenter. It's going back and forth, back and forth. So though it shows, the way it looks like is maybe that I'm converting R to S, what's really happening is my 100% R goes to 50% R and 50% S. So you racemized it, okay? And the reason this is a problem is because this S version of thalidomide causes birth defects in unborn babies. It's mutagenic. They come out with shortened limbs, and many of them end up dying in the womb. And it was a huge problem, and you can actually look it up on the internet. It's well documented. Okay, but this reaction occurs at physiological pH. So when the women who were trying to alleviate morning sickness would take this drug that was marketed to help them, yes, one of them did help, but the problem was the other enantiomer actually was harmful to the baby. And I've actually met a thalidomide baby. He's older, and yeah, he did not have a limb. He had a finger sticking out of his shoulder blade, and this was a huge problem. It was one of the darkest periods of chemistry, and it actually sparked a huge movement in pharmaceuticals to look into enantiopure products rather than racemic. Okay, so I just wanted to show you that this particular reaction, this tautomerism that yields racemization, could be big problem. So now I want to introduce to you the concept of making enolate ions from unsymmetrical ketones. So what I'm going to teach you is we have to make use of strong bases in order to do this. So at this point I might have given you tert-butyl ketone, and you know that that would be the only viable position to deprotonate. You have an alpha carbon that has a proton that tert-butyl does not. Or I might have given you a benzene ring. And you know that the only viable proton is right there to deprotonate. It's on an alpha carbon. Or I might have just given you simply a symmetrical ketone where it doesn't matter which one you take, it will yield the same product nonetheless. What I'm going to show you now is what happens when that ketone is not symmetrical, when there's two viable protons, one on either side to deprotonate, how you can make it go to the correct placement, okay? So in order to accomplish reactions using an enolate ion, a stable solution of enolate ion must be prepared, okay? You need to find a stable solution. Solutions containing stable enolate ions must be free of other chemicals or compounds that can react with it, as you wouldn't want this to happen, okay? They need to be free from other chemicals or compounds that can react with it. The point is that enolate ions are rather reactive, and if you have anything in there that might react with it, you are going to have a problem, okay? To make a stable enolate ion, you need a strong base. It needs to be strong enough to deprotonate something with a pKa of about 20, meaning it needs to have, the base needs to be of a pKa above 20. So what we're going to talk about is a molecule that I've already introduced in lecture 1 of this chapter, and that is LDA. Lithium diisopropyl amide, or potassium hydride is another one I didn't mention in this lecture, but you've seen it before in alkoxide chemistry, potassium hydride, KH, which by the way is K plus and an H minus. Recall that H minus is a hydride. And I just want to point out that at this point we've been using acid-base tautomerism, and we've talked about making enolate ions using acids or bases, but those acids or bases were in aqueous environments. Notice that I might have used a generic base or OH, or I might have used acid like H3O+. Well, now I'm introducing you to perhaps a more useful method of preparing enolate ions, not using aqueous solutions, but using organic solutions to ensure that nothing else is reacting. You may recall back in the LDA slide that I talked about in the previous video lecture that LDA is a strong base, yes, but it's non-nucleophilic, meaning it'll deprotonate and do the job and be done with it. It won't further react in a negative way. KH does the same thing, and that's why we're going to spotlight these two. So as it turns out, KH and LDA are both strong bases. They do not react with the generated enolate ion, and they're non-nucleophilic. Now these are going to be prepared in solutions of THF. You see that right there, which is not an aqueous solution. That's an organic solution. So any of these reactions that I'm talking about right now, the KH and LDA, they're not going to be in aqueous environments. You may recall that LDA is lithium diisopropyl amide. If you're confused about why that's called amide, go back and listen to the first video lecture of this chapter. Okay, KH, as I've already mentioned, is potassium hydride, and that is the structure of that. Recall that you can have protons, which is H+, you can have a hydrogen atom, or you can have a hydride. Proton is what you think of with an acid. It's electrophilic. Hydrogen ion you usually only see in radical chemistry. And then, of course, the hydride, which I messed up right there. It's a minus charge, isn't it? The hydride ion is nucleophilic and can deprotonate things, actually. Okay, it's basic, oddly enough. Okay. So LDA and KH as bases to form enolate ions. So what you might have is, let's say that you had this particular ketone. Now this is a symmetrical ketone I want to make note of, but you can actually have LDA and it will actually favor the product. So yes, it's in equilibrium, but it's kind of a minus 78 degrees Celsius, very cold. It is in equilibrium, but it heavily favors the product side, which is very important, by the way, to make note of, because you're making an enolate ion and it's actually a favorable product in this case. And so what you'd have is an Li plus as the counter ion, an H right there, and you would also have diisopropyl amine as your byproduct. And so of course what happened was you had your amide what it did is it deprotonated right there. That went right there, that went right there, okay, to generate the product. And KH would do the exact same thing, except for you would have a potassium counter ion. So it's going to come in, deprotonate right there. KH is so neat. This one actually is not in equilibrium, I want to make note of. You do both of these in THF. This one doesn't even have a temperature associated with it, so maybe room temperature is how they did this reaction. And what you would form is O. Just want to draw on the electrons in case you're having trouble following where things are coming from. So if you see O minus and a K plus, that's the product of using KH, or you might just see OK. You might just see like OK. And what that is O minus and a K plus, the counter ion, okay? And so the byproduct of this is, yeah, you use hydride anion to deprotonate, so that's H2. And that's a gas, and that just bubbles out of the solution. So hopefully you can see why that's not in equilibrium, okay? There's no H2 present in order to make it go in the reverse direction. It just bubbles out of solution. Okay, so both of these are viable ways to make enolates that are non-nucleophilic. You just generated it, and now you can use it for whatever reaction you may choose. So when preparing enolate ions from symmetrical ketones, it's very straightforward. Okay, if you have this particular molecule, diethyl ketone, or you may actually call it 1, 2, 3, 4, 5, so 3-pentanone. It doesn't matter if you take from that position or that position. They're both going to yield the same product. But whenever the ketone is unsymmetrical, you have to determine which enolate ion will be the major product versus the minor product, okay? Because there's two competing sides, and you have to evaluate the molecule to see which one is going to form. So the enolate that forms from the position with the least steric hindrance will be the kinetic enolate. It'll be the fastest form. You're going to see that with bulky bases such as LDA. LDA is bulky, and therefore it's going to only take from positions that have hardly any steric hindrance, the easiest to access. Okay, if you're really big, you're going to look for the easiest method to fit into. Okay, even if it's not necessarily the most thermodynamically stable, it's going to be the most accessible for your large molecule. Okay, so let's take a look at this particular ketone. This time I'm going to put a hydrogen here and a methyl here. Okay, so this is in fact an unsymmetrical ketone. Noticing that here's an alpha position and here's an alpha position. They both have protons. This side has 2 protons, this one has 1, and also a bulky methyl group. And so when considering this particular substrate, and let's say that you use LDA and THF, what it's going to do is it's going to deprotonate from the side with the least steric hindrance, which will be that side. So you're going to form what's called the kinetic enolate. And you're still going to have your H and your methyl here. And this one is going to be the favored product when using LDA. So whenever you have an unsymmetrical ketone and you use LDA, it's going to form the kinetic enolate, which stems from the side of the least steric hindrance. And we're talking about the alpha carbon compared with respect to the carbonyl group. The kinetic the enolate that forms the most substituted double bond will be called the thermodynamic enolate. You're going to see this with small little bases such as KH. Because you know hydride's very small, right? Versus LDA is very big, those 2 isopropyl groups. So what's going to happen in this is you take the same molecule, this particular ketone with the methyl group, and you react it with base, and let's call it KH and THF. What you're going to find is it's going to form the thermodynamic enolate. And what I need you to notice is that it's a CH3 there. I'm going to try to highlight this as well as I know how to. Let me make sure I get a good highlighter out. Okay, there we go. So look at the kinetic enolate case. Notice that this double bond, it has 3 different attachments to it. Okay, so if you were to look at the left side of that double bond, it has 1 attachment and 2 attachments on the right, whereas if you look at the thermodynamic enolate, it has 4 different attachments. You may call this tetrasubstituted if you like, but I'm going to try to outline what I'm talking about. Look at the kinetic enolate. It has, first you need to find the alkene. First I need to get off the highlighter mode. Find your alkene and put a dot on either side of it. And then notice on the left side dot how many bonds? There's only 1. On the right side dot there's 2. So you notice it has 3 attachments to it. You might call that trisubstituted. Now remember, the more substitution you have on a double bond, the more stable it is according to Zaitsev's rule. And so look at the bottom enolate. Notice that if you identify the 2 carbons that compose the alkene, you have 2 attachments at the top one and 2 attachments at the bottom one, which makes it 4 total attachments, which makes this a tetrasubstituted. So this one is the thermodynamic enolate, because it stems from the most stable carbocation, whereas the kinetic enolate would be the most easiest one to access. Okay, the quickest form would be kinetic, aka it's the one that has least steric hindrance, if you will. So in one case, you're looking for the stability of your alkene. That's your thermodynamic product. You can only access that when you have a small base, such as KH. The other one would be your kinetic product, in which you don't form as good of an alkene, but you have an easier time getting to the proton to make it the kinetic product. Okay, fastest formed. So here's a slide for you. The kinetic product is favored when the reaction is not in equilibrium, as it takes advantage of the different rates of competing pathways. Okay, so it can't be in equilibrium to be the kinetic control product. Okay, that's why oftentimes you'll see this you're doing this reaction at low temperatures. It's very cold, -78. It's slow. It even halts the equilibrium. Okay, so it's not going back and forth, back and forth. It's just saying, all right, ready, set, go. And the kinetic one's formed fastest. And if you're not going to go in the reverse direction, that one's going to be your major product, because it's going to win the race every time, because it comes from the most accessible proton. Okay. Oftentimes you're going to form the kinetic product when you use a strong, bulky base, such as LDA. However, in contrast, you have the thermodynamic product. It's favored when the reaction is in equilibrium. Okay, so you're going to see arrows that go back and forth. And even if the kinetic product is formed, the energy of the system eventually settles with the formation of the most stable species, aka the most substituted double bond. It's called the thermodynamic enolate. Oftentimes you'll see higher temperatures in order to promote the equilibrium, because what happens is, even whenever you do form your thermodynamic enolate, you are forming some of your kinetic enolate. It's not going to say, oh, I only need to go to this position because I'm supposed to form the thermodynamic. It's going to form both, but keep in mind that as it goes through equilibrium, it's going back and forth, back and forth, back and forth, and over time it fully populates the thermodynamic product. Okay. Another key trait is you might want to use excess ketone when accomplishing these. I'll talk about that in the next slide. And also, you might want to use a strong, small base in this process. Okay, so earlier in the slideshow I had mentioned that you need to have that KH is irreversible. That was a mistake. Using KH can be reversible. It can be in equilibrium even though the H bubbles out of solution. Okay, you just might want to add excess base, and maybe adding this excess ketone can accomplish your task. But I just wanted to point that out, that was a mistake I said. And if you only use one equivalent, it's not going to be reversible. But if you use more than one thing, or excess ketone, or just modify the reaction conditions ever so slightly, you can cause this to be in equilibrium. So just wanted to correct myself in that. Here is a general scheme on the right-hand side of kinetic versus thermodynamic, maybe what you're looking at with the equilibrium. Okay, so take a look at those schemes when you get a chance. I wanted to point out also the reaction coordinate diagram. So remember these, you have energy on the y-axis, and you have reaction coordinate on the x-axis. And let's start with your kinetic enolate, okay, the fastest formed. So what you have is your starting material right here. It's going to go through this particular transition state that is pretty high, and then you wind up with products, right? So remember, this is called the transition state, and this would be starting materials, and this would be product. Now, let's transpose on this graph the kinetic version. So you still have the same start materials, the same position, but what's going to happen is, because it's very hard to get to that proton, it's going to take more activation energy. It's in a more bulky place. But then notice you form a more substituted double bond, meaning that the product is actually more stable in energy. Notice that the product of the thermo versus the product of the kinetic is lower in energy. And so that's what's happening. So notice right here, you have a lower activation barrier. This forms the isomer faster. Which is the kinetic. And so in terms of our chemistry earlier, which you're looking at is this one. Okay. Now, to contrast that, notice that the bottom graph, at least in terms of the thermo product is what I'm trying to say, more substituted double bond. Equals more stable thermodynamically. So we're looking at KH in that case, and in the top, I don't know why I just drew a K, KH, and in the top case we are looking at LDA. So that's how the energetics works in this, and it's a transition state for both right there at the hump. Adding excess carbonyl compounds favors the thermodynamic enolate. So you may recall a couple slides ago I had mentioned that, and so I wanted to explain to you what the principle is behind this. It's kind of interesting. So let's say that you had this particular ketone. You have this H right here, and you have the CH3. It's the same ketone we've been working with. And let's say that you end up forming the kinetic enolate. Now remember, we're in equilibrium, right? So we're actually saying that adding excess carbonyl compound favors the formation of the thermodynamic enolate. So go slow, listen to my words very carefully. This was the kinetic enolate. Why am I drawing the kinetic enolate whenever I'm trying to tell you that adding excess carbonyl compound favors the thermodynamic? Well, again, you may want to pause and listen to the terminology that I'm using, but whenever you form a thermodynamic enolate, there is going to be a lot of kinetic enolate formed as well, but because it's in equilibrium, it's going to be shifted back towards the thermodynamic enolate and then populate the more stable isomer. So what I'm trying to say is this. We are doing a reaction where we're making the thermodynamic enolate ion, meaning the most stable double bond. But in the process, we just accidentally made some kinetic enolate. That's not good, but because we're in equilibrium, the question is, how do we get it to go back? We don't have any more KH. Well, here's how it works. I just made some thermokinetic enolate right there, and it needs to be converted back into the thermodynamic enolate through equilibrium. The way it does that is that if you have excess ketone, say you added 1.5 equivalents or 1.2 equivalents of your ketone starting material, what can happen is this enolate ion could drop down, look at the mechanism, then that can reach out, go right there. That can go there, and that can go there. Notice it is acting like the base. It is acting just like the KH would have acted. Now the H2, the product of the deprotonation using a hydride ion, has bubbled out of solution. It can no longer serve that purpose of deprotonating because it's gone. But having excess ketone allows this reaction to continue forward. Now we're in equilibrium. Notice what just happened to your kinetic enolate is that you just reformed a ketone, which can then be converted to thermodynamic or kinetic, and repeat this process, and then you just populated a thermodynamic enolate. Check out the mechanism if you are struggling, and so on and so forth. That's your thermo. So notice how in this process, because you had excess start material ketone, you essentially were able to reconvert your kinetic back to thermo, and process goes on and on and on until eventually, after so many cycles, you have a majority mixture that has a thermodynamic product overwhelming the amount of your kinetic product. LDA versus KH. So as previously mentioned, LDA, lithium diisopropyl amide, not the functional group amide, is a strong bulky base that favors the kinetic enolate when deprotonating unsymmetrical ketones. Let's check out this particular ketone. Yeah, let's make it 5. And we're going to do LDA THF minus 78 degrees Celsius. And what you're going to form is this. And that would be your kinetic enolate, okay? It stemmed from the least substituted side, or the less hindered side. And that's going to be 100% of your product, okay? Kinetic product, because you have 3 easy to access CH3s right there. Look at the starting material, versus 2 CH2s right there. So statistically there's less, and then also there's more molecule around it to cause bulk. So it's going to be hindered in various ways. Easier to make LDA deprotonate where I have the circle already right there, okay? Of course, if you form the kinetic enolate ion using LDA and then warm the solution, it would become the thermodynamic enolate ion with a thermodynamic enolate with a lithium counter ion. So notice I kept this reaction that I'm starring at minus 78, but let's say I would have had this particular ketone, and I did LDA THF minus 78 degrees Celsius. This is based on an experiment, by the way. That would form the kinetic product, but let's say I kept the solution and I warmed to 25 degrees Celsius. It's room temperature. What happens is you actually form the thermodynamic enolate right there. And so notice in warming causes equilibrium to kind of kick back off, because at minus 78 it was frozen, but now you added enough energy to overcome that activation energy barrier as I drew it in the reaction coordinate diagram. Thus now you're in equilibrium. Now you can actually populate the thermodynamic enolate. So make sure whenever you're trying to draw the kinetic enolate that look at the temperature. If it's cold and remains cold, you know the equilibrium's frozen. It's going to form the fastest, most easiest to access enolate, aka the kinetic enolate, which again is favored when using a big bulky base, non-nucleophilic bulky base such as LDA. KH is a strong small base that favors the thermodynamic enolate when deprotonating unsymmetrical ketones. So we're going to finish this particular lecture doing some practice. And so it wants us to write equations showing how you prepare the kinetic and thermodynamic enolates from the following ketones. So let's start with A. I'm going to redraw this particular ketone. Notice it has a phenyl group. It also has an H right there. I'm redrawing it in a more vertical perspective just because I'm more used to seeing it that way. Okay, all I did was I tilted it a little bit. And if I wanted to make the kinetic enolate, I would just say LDA THF minus 78 degrees Celsius, making sure not to warm it at all. And I know I would form the kinetic enolate as shown right there. So I draw out the benzene ring for you. Okay. And then if we wanted to make the thermodynamic enolate, which I hope you're actually doing this at home without just watching me do it, but that you're actually trying this on your own. I would, let me just emphasize that the equilibrium would actually favor the products, but I would use KH, THF, room temperature, let's say 25 degrees C, and then I should have confidence that I would form the thermodynamic enolate. You have it. Now in the not number 2, but part B, we have this ketone. Okay, we take this ketone, it has an isopropyl on one end and an ethyl on the other, noting that both have alpha carbons that bear hydrogens, but one's in a bit more of a bulky surrounding, has more of bulky surroundings than the other. Keep in mind the ethyl is more easy to access than that bulky isopropyl group surrounding this particular proton. And so if I want the kinetic product, I'm going to use LDA, THF, minus 78 degrees C, and I should end up getting my kinetic enolate. And to finish this one off, let's make the thermodynamic enolate. This one is going to be in equilibrium. We're going to use KH, THF, 25 degrees C, aka room temperature. And we're going to form the more stable double bond after heating it up in equilibrium. Thermodynamic enolate. So, class, that's how you make enolates. That's how you judge between unsymmetrical enolates, the kinetic and thermodynamic products, and the bases you might see with each one. I hope this lecture made sense. Always feel free to reach out if ever you have any trouble. Have a blessed day.